So we were studying trying to introduce N-path filters, and after the class there were some questions, so I thought maybe I can quickly address them also. So where we ended last class was to show you that, let's say I have an LPTV network at omega s. You have an input d power j omega naught t, and you have a clock, right? So this clock is the thing that is giving us this periodicity. Then if I copy this LPTV network, and this is also switching at omega s, but this clock I delay by Ts by n and apply here. And I do for n of them, and I add them up and add the outputs up. Then here we saw that the H naught adds up, H1 goes to 0. Similarly, H till Hn minus 1, it goes to 0. Then again, Hn adds up, right? So mathematically we saw that, and intuitively the explanation is, what is this envelope? What is this delayed clock doing? So if you think about it, just like in an RC time constant scenario, for example, when we had this, let me just say that this is an RC time constant scenario where R goes like this. Right? So this is 2R, this is R. This is the first example that we started off with. So in the first path, the envelope would look like something like, so I should not, I mean, if you apply sinusoid, it would look like this, and then probably increase, and then again go like this, and then this will repeat, right? So this guy will repeat if this goes like this, and so on. So this is the first path. In the second path, what are you saying? What we are essentially saying that this entire thing is delayed by some time, which essentially means that your envelope also gets delayed by equal amount of time. By the way, the envelope is not this. Envelope is this. Correct? Okay. And when you keep doing this for n number of times, n minus 1 number of times, and you come back to n, then this envelope is going to repeat again. Correct? And these envelopes, it is equivalent to saying that all these envelopes are delayed with respect to its previous envelope by a phase which is basically 2 pi by n delayed. Correct? So if you assume that this is one cycle, which is a phase of 2 pi, right? One cycle has a phase of 2 pi. If you delayed one envelope by 1 nth the cycle, the phase delay is essentially 2 pi over n. And if you keep on adding 2 pi over n plus 2 pi over n times 2 plus 2 pi over n times 3 and so on, and you have all n of them added together, or n minus 1 of them added together, then you are going to get 0. Just that the non-zero value will come when you come back to the nth cycle again. Does that make sense? It's like phasors that are lining up, right? The example that I gave in the previous class is like phasors lining up. That is the reason why you get this H0 to be H0 and Hn to add up, and all of them to go to 0. And that obviously has advantages that we discussed, that if you want to filter, right? If you want to filter, if you want the bandpass characteristics to be filtered, then obviously having such a scenario is always more helpful than having tones which are nearby. Nearby in this case is essentially omega s, 2 omega s, 3 omega s, even though one might argue that 1 gigahertz and 2 gigahertz are not necessarily nearby, but it is always better to have something at 1 gigahertz and maybe at 4 gigahertz rather than 1 gigahertz and 2 gigahertz, right? So the putting a filter will obviously help such scenarios, okay? Okay, and another question that came up was, what is the relationship between this circuit and the RC time constant switched RC circuit that I ended up with, right? So let me also briefly talk about it. So can you comment on what is the relationship between this circuit this whatever block diagram we had and this guy, and let's say this is my output V naught. So is there some sort of correspondence between these two cases? The LPTV is a switch. Yeah, the LPTV is a switch again. So this is you assume this to be S of t, this to be S of t minus Ts over n, and so on. So again, assume that if this is not obvious, then maybe I assume this. Okay, let's do this. So we understand that this voltage is the voltage across the capacitor multiplied by S of t. Correct? Where S of t goes from 0 to 1. So instead of doing this, if I say that I do this. This is also R, this is also R. And this is S of t, this is also S of t. Can you comment on this voltage? Yeah, the fact, let's forget about the half part for the time being. It will be also multiplied with SRST. Correct. It will be 0 at off. Correct. It will be 0 at off time, right? So this is basically what? If I say V0 is VCT when S of t is high, and this is equal to 0 when S of t is 0. Correct? Agreed? So this is nothing but this network. Isn't it? Make sense? Okay. So I'm disregarding the fact that these are two different R's. I'm disregarding the fact that maybe at DC there will be a factor of 2 difference. If we disregard that fact, then at least we agree with this. Okay. Okay. So if this is the case, then can I say that I have another of these? This is S of t minus n, S of t minus n. And this I connect it here. And can you now comment on the fact that if, let's say this is called V01, I call this V02, are V01 and V02, I mean, does this path and this path interact with each other, or they are independent? Provided the switches are non-overlapping between the top and the bottom phases. It's non-overlapping. They are not interacting. These two paths are not interacting with each other. We agree with that, right? Fine. So the fact that I have put the bottom part here does not in any way affect the top part of the network. Correct? Okay. So if I do this n number of times and I add all of these up, I am going to get that same operation that I have been talking about, right? That H0 will get added up and everything else is going to go to 0. Okay. Oh, sorry. Yeah, thank you. So, correct. This is wrong in multiple ways. Yeah, okay. Fine. Okay, so if you agree with the fact that here we are going to have H naught and nothing till H of n minus 1, then, and we agree with the fact that this setup is the same as this setup with another switch, then do you agree with the fact that this total setup is the same as this setup? I mean, other than the fact that I have a factor of 2 maybe different, the right and the light and the left, because I mean, there is an odd by odd division that can happen on the right, which cannot happen on the left. It's not clear? Naren? Okay. Okay. Anybody else? If it's not clear, then I will try to attack it from another angle. That's why I'm asking, is it clear or not? Fine. Can I move on? Okay, fine. So if we agree with this, then we should agree with the fact that this can work as a decent bandpass filter, right? And the bandpass filter bandwidth, the close-in bandwidth can be made as sharp as possible. I mean, all the good things of an n-path filter, that is, you can keep making the bandwidth sharp by increasing n, by increasing c, or by increasing r, whichever is more convenient. Another good thing is the center frequency is totally programmable, electronically programmable, right? You give the clock and the frequency of the clock decides the center frequency, right? Which is unlike any LTI filter that you can think of, right? So naturally, when in a domain of electronics where you would like to control everything electronically, why not this, right? So why should we limit ourselves by having a constant center frequency which is based on the values of the components? And I don't know whether you have been exposed to this in 610, but in general, all these components also have variations, right? So let's say you have L and you have a C, and if you do an LTI filter based on an LC, and you target, let's say, 1 gigahertz bandwidth, and you fix your L and C to whatever values, and it's quite possible the L and C can vary by 10%. Right? And if they vary, then obviously your center frequency is going to vary. Right? 10% is probably an exaggeration, but you get the idea, right? And if you are trying to get a very narrow band filter with L and C, and the center frequency varies, it is quite possible that you don't capture any of the intended input. Right? Your intended input that you are planning to capture might fall out of band if the center frequency varies slightly because of the variations of L's and C's. Right? So that is why when you do LTI-based filter, it is not sufficient to have only one L and one C. That's why people have options to tune that center frequency with multiple L's and C's. Let's say you You tape out and you fabricate, and the chip comes back. You targeted 1 gigahertz. It comes out to be at 1.002 gigahertz, right? Or 1.02 gigahertz. Right? 20 megahertz off from whatever you want. And let's say your bandwidth is itself 10 megahertz. Then you're gone, right? Your target frequency is gone. So that's why you have multiple L's and C's in parallel. Not necessarily L always, but mostly C's, to tune that center frequency back to wherever you want. This is all done at a post-processing level, in the sense that chip comes back, you test, you see it in the spectrum analyzer where the center frequency is, and then you shift the capacitor bank so as to shift the center frequency. And you either do it by looking at the spectrum analyzer or not. That's a different thing, but this has to be done, right? Without that, none of your cell phones are going to work. Okay, so now naturally, from that perspective, now if you tie this argument with LPTV bandpass filter, you see that there is a significant amount of advantage, because the clock frequency is set by something else and the clock frequency is not shifting. It's a different matter that there is probably a PLL somewhere in your system which is trying to lock the center frequency to certain certain fixed value, but that anyways is there. We are not adding any hardware base in order to achieve the bandpass filtering. So assuming that center frequency is fixed, which means that any tuning of the components are not required. It is independent of component variation, right? In a sense, it is independent of component variation. It is electronically programmable. You can get arbitrarily sharp filter, looks like, right? So, but I mean, there are issues which are second order effects, which I am not going to talk in this course, but looks like this has a fair amount of merit to replace the standard LC-based filtering that we use in many bandpass filtering applications. Okay, and these are, becoming more and more common in multiple different types of topologies as the years pass, right? Yes. There is no benefit. I just told you to give you an analogy between why this left and right are similar. Correct? In this context, there is absolutely no benefit. In fact, there is, if at all, there is a problem, because you will have, gain will go down by a factor of 2. Right? So, I mean, the reason I showed this, because it is easy to appreciate how the adding up things is happening, in the sense that even though I showed this adding up like this, in the output, I can simply say that I have a single R. This is connected and I have a single R. Because this R is being driven only by one of the kernels, right, at a time. It's not necessary for me to have a separate R for each kernel, right? So you can think of that the currents are getting added up at each phases, correct? And this is exactly similar to this case, where the voltage across this capacitor, here, just as the voltage across this capacitor is multiplying by S of t, here also the voltage across this capacitor is getting multiplied by S of t. Correct? And in wherever the S of t is 0, right, where instead of getting multiplied by 0, it is getting multiplied by the voltage across the next phase, next kernel. So you don't see a 0 at the output anytime, but with respect to the analysis for each of these kernels, you can think that S of t is getting, you are multiplying each of these kernel by S of t, where it goes from 1 to 0. Wherever you have a 0, the next phase is getting non-zero, and you are adding them up, right? I mean, I'm not sure whether I'm being able to convey it properly, but let's see. So let's say what I'm saying is, let's say you have an S of t here. You have S of t minus n here. I'm showing two phases. So at the output of one phase, you get what? You get something like this, and then it goes to 0. Then you get something like this, goes to 0 and some, right? At the output of the second phase, you see 0, then something like this, 0. When you add all of them up, what do you get? When you add all of them up, you get here, then you get there, then probably something was here, then that, and so on. and this guy repeats, right? Isn't it? So with respect to time, you get something like this. So this is equivalent to each of the phases have been gotten multiplied by S. Each of the kernel, each of the capacitor voltages have gotten multiplied by S of t, which is time shifted for each of them, and then you add them up. So as far as the analysis is concerned, it is exactly the same as multiplying by sequence of 1 and 0, right? And then you add them. Okay. So that is why, I mean, strategically, this extra switch was put in all the analysis till now. Even though this switch was not necessary, right, in finding ht of tau. If you recall, it was not necessary for us to put, I mean, the h2t of tau for one kernel would have been exactly the same, regardless of whether this switch would have been there or not. But I intentionally put it so that everything makes sense when I add all the kernels up. Okay. Convinced? Okay. Fine. So now I'm going to tell you something which, after knowing that, you probably will feel a bit cheated, because there is a way of making all this analysis much simpler. Yes. Come again?
So SPT is not there. When ST is off, other node it goes to 0. It won't go to 0.
Which node it will not go to 0? So
Before ST it won't go to 0.
yeah, it won't go to 0. Correct. Before ST, it won't go to 0.
If there's a switch, it will go to 0.
Correct.
So like if you're taking from there, it would make a difference, right?
Correct. It would. Yes. But what is your point? But we are not taking the impulse response. We have whatever we have calculated is for across the capacitor, not this point. So the way we went about doing this, we never calculated the bandpass response at that particular node for n paths. Right? We did it for one kernel, and then said that if you add everything up, it behaves like an n path. Correct? So now I understand your point. So your point is, let's say I find out the response for this particular circuit for this node, which we have not done. So note that if the network is like this, then I cannot say this voltage is a VC of t multiplied by S of t. Let's say VP of t. I cannot say VBP of t is equal to VC of t multiplied by S of t. Can I say this? I cannot say this. Because in this case, when S of t is 0, this voltage is VIT. Correct? So, but to make sense of all the n paths adding up without causing any trouble, I needed this VBP of t to go to 0. So that's why I put that switch. For making sense of the analysis, you need the switch. But when you put things together, that switch is not required. So the point is this. So analysis will become, you can still do the analysis, just that it will become slightly more complicated. So I can still have, let's say I find out the response at this node, right? Somehow, right? The response will not be this. It will not be VP of t VC of t multiplied by S of t. It will be something. I find this out. I find out the same thing for this guy, right? Then I add up. You are going to get identical results as this, provided you connect them physically. But when you do this, this is not the same as this. Because Because now in this case, when this switch is off, this is input, direct input without any attenuation. But when this switch is on, when the other one was supposed to be off, this is supposed to be this voltage, correct? So in a way, you see that you have to take into account that now the input is interacting between two kernels. If I use the bottom analogy, correct? So in the sense that in one is, so the voltage, you want this voltage to be only the voltage across the capacitor, which is being controlled by one kernel. This should not have the information of the other kernel, correct? So, but if I do whatever we have been doing here, who sets the voltage across the other end of the switch? I have two information there. The top one is essentially the top case is essentially VI when the top switch is off, but at that time the bottom switch is VC2. So the output is VI plus VC2 in the second phase, but that's not that's not similar to this operation, correct? So because I wanted this VBP to be only the voltage across the capacitor at that phase, nothing else, I had to ensure that the contribution of one of the paths goes to 0. So hence that switch was strategically placed. I did not tell you at that time, but that was the reason. So that's why these two are not equivalent. These are not equivalent. But the other cases. Yes. But good question. Now, if you have time, you can do the analysis of this. I mean, its process is the same thing, but I mean, you will have to take into account another phase. If you keep as, yeah, if you keep so basically I'm pulling that voltage to 0. If I pull that voltage to 0, I don't have to think about it. Like I have to go to the next phase and think only about that phase. Otherwise, I have to think about this phase separately, right? Make sense? Okay, fine. So next part, what I am going to talk about is this, how to simplify this whole analysis, right? So here again, we'll go back to interreciprocity that we studied long time back, right? So what was the benefit of interreciprocity or rather Telegrams theorem and all these things? One of the reasons we did that was because it helped us analyze it. Not only it helped us analyze situations where we had, I mean, maybe the input is connected at somewhere else. It also helps us analyze situations where we had multiple, for example, in noise analysis, where we have multiple sources. And we, instead of finding out transfer functions n number of times, we could find out the transfer function once and add them up, right? So it helped analyze there. So now you are going to see another useful effect of LPTV, how it helps ease the analysis of these type of networks. Okay, I'll start off again with the same analogy. That let's say I have an LPTV net. Forget about LPTV network, any network, right? So any network. Let's have a capacitor L and C. I'm not putting LPTV till, I'm not putting any switches as of now. We're shortly going to put it back, but let's assume this is what it is. What did we do in Telegrams? We said that we have an hatted network here. This is an N, this is N hat. We said that if I apply a voltage here, we see a voltage there, it is equivalent to applying a current here and seeing a short circuit current here, right? Provided what? Provided one condition gets satisfied, that is whatever is inside the network. For that, if I have an element which has voltage Vk and current Ik, these are the voltage Vk hat, current Ik hat, provided Vk times Ik hat should be equal to Vk hat times Ik, right? So if this is true, then we could, then reciprocity or interreciprocity was valid. Correct? You recall? Like long time back we did this. Okay. So then if we didn't have any control sources, if we had only R's, then we said that this was trivial, because if we have R, if only R is present, then it's Vk is equal to Rk times Ik, right? And similarly, Vk hat is also equal to Rk times Ik hat. So hence this is trivial. This relationship is valid. We can use interreciprocity. Then a question came, if I recall explicitly, the question came, what about capacitor? What about capacitor? What about inductor? At that time, I said that you can use phasor, right? You can use phasor. In the phasor domain, this is still valid. But I bypassed the question that I'm going to answer now. And the question is this. If you have a relationship, let's say you have a so fundamentally, your capacitor and a resistor, or a memory element and a resistor, is different from each other with respect to the fact that one stores a time information and other does not. What I mean is that this is not an LTV system by any means, but there is a memory effect in one and you do not have a memory effect in another, right? So in a sense, when I do a multiplication of this in phasor domain, in S domain, right? So when I do, so I probably should be careful with the notation. Let me write it. Now I'm going to use time and phasors, so I'm going to use a small and large notations, otherwise I'll get confused. So in phasor domain, I understand that, or in S domain, I understand that, so this is in S domain. Vk of S is equal to Zk of Is, Iks, right? Similarly, Vk hat of S is equal to Zk times Ik hat of S, right? This is in phasor. And we do the same thing in S domain for whatever we did, and we are going to get reciprocity, interreciprocity in S domain or in J omega domain, right? There's no trick to that. But now if I use the same thing if I use the same analogy in time domain, what do I get? So when I say Vk times Ik, Vks times Iks, this is in S domain. In time domain, what does it mean? I'm doing convolving, right? I'm convolving the time domain. So I'm basically saying I'm doing Vk times, I'll not use tau, let's say I use eta, times Ik times, I don't know, maybe something. Oh, let me use tau here, I'll use eta there. Okay, so yeah, Vk times tau times Ik times eta minus tau d eta, and from, let's say, 0 to t. Correct? So this is essentially your output in time domain. So far, so good. We have not reinvented any wheel. This is what it is. We know that very well. Now, note that for reciprocity to be valid, we are saying this is Ik hat. This is for the second network, which means this is for the nth network. This is for the hatted network. Correct? So again, forget about the integration. Integration is basically adding up in memory, but if you only concentrate on Vk tau times Ik eta minus tau, what can you infer? That I know that interreciprocity will be valid at Vk in the S domain. But naturally, which means the interreciprocity should also be valid in the T domain, time domain, because they are equivalent, right? Just a different representation. But for that equivalence to hold, what should I do in time domain to those two networks? In time domain analysis, what am I telling? Convolution is fine, but are the two networks being analyzed at the same time? What is the time what is the time argument of the nth network? Tau. What is the time argument of the Hatted network? Eta minus tau. So are they being analyzed at the same time? No, right? It is crucial to understand this difference. The nth, for interreciprocity to be valid, strictly speaking, the original network and this interreciprocal network are not evaluated at the same time. Okay. And note that elegance does not say that they have to be evaluated at the same time. In general, elegance is true for any time, as long as the graphs are same. But if we have to establish port variable, port equivalence, right, then we need more stricter alignment. And for that, we need this. Correct? So again, why? So what is it saying? It is basically saying that this network is being evaluated at some time. If I say T, so this network is being evaluated another time, T minus eta. Correct? Or rather eta minus T. Not. Right? Make sense? Make sense so far? Now the question is, why don't we bother? Why don't we bother about, so far, I mean, we have done analysis of elegance and everything. We never bothered about this eta minus T or something. The reason we didn't bother is this. So if it's an LTI network, right, you apply an input and you check the response at the output. You apply an input, let's say at time Ti, and you check the output at Ti plus delta T. And here, what are you doing? You apply, if I apply the input now, by the way, it's a different time, right? Second network is being evaluated at a different time. Okay. So I'll have to apply the input at some Ti, but Ti should be in this case what? Eta minus Ti. Correct? So this input has to be applied at eta minus Ti, and the output will be checking at okay, hold on. I have. Sorry. So if I have to do an equivalence, so which means that, so this okay, so let's see. So this Ti here, whatever is happening at, the way we should think about it is this: whatever is happening at T here is happening at eta minus T here, right? So effectively, that's what we are doing, right? So this Ti here gets transformed to eta minus Ti, and this gets transformed to eta minus Ti plus delta T. Correct? So the reason, now comes the argument why we did not care. The reason we did not care is, what is the difference of time between the application instant and the observation instant in the interreciprocal Hatted network? It is still delta T. Right? In this case also, there is no, causality is not getting violated in any way. In the first network also, I applied the difference of observation and the application was delta t. In the reciprocal network also, the difference between application and observation is delta t. Just that the exact application time changed, the exact observation time changed. But in an LTI network, it does not really matter. The response does not change if both the observation and the application time change together. It's only the difference that matters, right? So it does not matter if I apply this at, if eta equal to 0 and I apply this at Ti plus delta T and see it at Ti, or I apply it at Ti or see it at Ti plus delta T. All are equivalent. Okay. So now can you guess where am I going with this? In case of an LPTV or LTV network, it is not equivalent, right? It is not equivalent in an LTV network, which means that in an LTV network, you have to take this into account. If you do, you have to do interreciprocity, you'll have to flip the time axis and shift by eta for it to make sense. Okay, I promised you it's going to be easier. Hold on, it's going to be easier. Okay. So the why is it going to be easier? So what I am saying is, so in LPTV, we need to flip the time axis and then shift by whatever eta or whatever, right? So whichever time I am interested to observe, I have to shift by that time, right? So, but the main thing to understand is that we have to flip the time. In the interreciprocal network, the time for what? The time for which the time at which the network is changing, right? Because the LPTV network is changing with respect to some other input which is changing the envelope. That time will, that flipping has to happen. Okay, fine. So let's do, let me tell you without keeping you in suspense what it looks like. So let's say I have the same thing we did. We take the same example of this guy. So this is S of t. So in an here we are applying the voltage impulse here. We are observing it here. Correct? If I have to do an interreciprocal equivalent, then this guy remains as is. But I have to apply a current impulse here and see the current through this, right? If interreciprocity is valid, right? Then this is what we will observe. Sorry, this is like this. Okay. So I mean, in this particular case, this is not required also, as I made the point. So let me not make things overly complicated. So this is S of t. So what should this be? If I flip this, this will be S of minus t, right? It should be S of minus t. And then this value, what is eta essentially? If you look at it, what does eta mean from this perspective? Eta is the observation instant. Correct? I mean, when I'm integrating from 0 to t, eta is the running variable. Tau is the running variable, but at any point of time, the eta gets kind of replaced by t. So it's the observation instant, right? So in our case, we are doing a t on. Correct? So, but the t on thing, let's keep at bay for the time being. The key thing to understand is that S of this is going to be S of minus t. Okay. So what does S of minus t look like? So this was time equal to 0. So 0 remains 0. So what will S of minus t look like? So this guy will come this way. And This is TS. So this will be TS minus T on. This will be TS minus of TS plus T on, and so, right? And here we were observing, where here our observation instant for all the analysis that we did was here at T on, correct? Now, again we go back to this network. So we are applying a current source, and we are, obviously the application time changes. The application, the application location changes. But what about the application time? Should also. So note that here we were in the original case, we were observing at T on and applying tau before T on. In this case, what will we do? If everything flips, we'll be observing at, we'll be applying at T on and observing at after time tau. Right? Okay, so look at here, right? So here, what are you doing? We are applying at Ti and observing at Ti plus delta T. And we are moving delta T. Correct? So this Ti is equivalent to, in the original network, that Ti was equivalent to the point we chose the value, we were planning to find out the impulse response is whichever point that we want, right? So that impulse response was at, if we are initially planning to look at, if we are initially planning to observe things at T on and apply something at tau before T on, because everything has flipped, right? Because the input and output ports have also flipped, right? So which means that the running variable is not at the input port, right? Running variable is not at the input port, running variable is at the output port, right? Things that is shifting is at the output port. And if you're not convinced, look at this, right? So here, in second port is fixed. This guy is moving in terms of time. The promise of why the analysis become easier now is this, because till now what we have been doing, we are fixing the observation instant and moving the application instant. But now in interreciprocal network, I can fix the application instant and move the observation instant. Right? And that we know, that we are comfortable with. Right? So which means that now I can fix. So here I can apply my impulse here. So because this gets translated to this, right? And because I have flipped and shifted, right? I flipped and shifted. I flip and shift the observation time. Instead of flipping the entire thing and moving by T on, right? It is equivalent to saying that I flip and I move my application time by T on. So that's what I am doing. So here I am saying that now I am going to apply the impulse here and see what is the effect of that impulse at the output. How does it go as I move forward in time? Moving forward in time is always easier to analyze than moving reverse in time, moving back in time, right? So a quick example, let's do the same analysis here. Let's do the same analysis here. So this network is what now? So I apply delta T here. this is S of minus T, C R. I'm interested in this current. Now, correct? Okay. So again, so I have applied the impulse here. When I apply the impulse here, what is the voltage that accrues across C? 1 over RC, correct? Because switch is on, right? I mean, sorry, voltage is 1 over C, the switch is on, and the current that is going to flow is? So yeah, right. So this is basically this. When the switch is on, this is basically this, right? So what is the current through this R? 1 by RC at time t equal to 0. Then after that, to the minus tau by RC, right? So now again, this tau is basically the running variable that changes, right? Whichever was the difference between the application instant and the observation instant, right? So this is the tau that runs. So now your output will look like this, goes here, drops, and then goes here, starts from here, drops, and so on. Does it make sense? Okay, so if that does not make sense, then let's see. So when S of t is closed, it evolves like this, correct? When and how long will it evolve? For till t on, correct? So it will evolve and it will go to 1 over RC e power minus t on over RC, correct? Then the switch opens. In the flipped version, now we're talking about the flipped version, the switch opens, right? Switch keeps opening, which means the voltage across the capacitor is retained, correct? Voltage across the capacitor retains and the switch closes. And the voltage again, it starts discharging like this and so on. So this is a far easier way to see how the things evolve rather than fixing your observation time and moving the, right? So how we came out to this is a more involved way of analysis. But if we agree with the fact that this is valid, then you see that the way of doing analysis becomes much simpler, right? Then you do whatever. Then you do, once you have HT of tau, whatever what do we get? This is basically equivalent to HT on of tau, right? Right? In the original network, we were observing at or fixing my observation time at t on. In the new network, my application time is at minus t on, and we are observing, right? So key takeaway, we'll stop here because I have to do the SRS. The key takeaway is when we keep moving, when we do interreciprocal network for an LPTV system, we'll have to flip the time. That does not mean that we are doing any non-causal activity. Okay, so we are flipping the time, but we are keeping the difference between the application and the observation still positive. Okay, in principle, you should always flip time, regardless of LPTV or LTI or LTV. But it does not matter in an LTI system whether flip time or not, because that difference is difference with the final output is only dependent on the difference, not the application, not the observation time or the application time. But in an LPTV system, you do not have that luxury. You'll have to flip. And note that you have to flip in an LPTV system with capacitor effect. I mean, that is, or in having memory effect. If there is no memory, there's no flipping necessary. Because this convolution and all those things came because you had a memory. Otherwise, the alignment will only happen at only one particular point of time. There's no convolution necessary. But that's besides the point. The key thing is to understand is that in an LPT, flipping is the generic thing to do. Right? Flipping is a generic thing to do. In an LTI system, you can get by without flipping. In an LPTV system or LTV system, you have to flip when you are doing the analysis in time domain. Okay, and as long as this is true, then obviously all the other things of reciprocity, interreciprocity is true, right? So if you have if you have elements which are interreciprocal, which means which you have control sources, you flip the control sources because they are LTI anyhow. Just that the time information that is embedded in the network is in the form of how the switches are changing. That switch changing time interval has to be flipped. Okay, so we'll talk about it in more amount of detail in the next class, and I'll post the assignment today. Thank you.